Hi everybody, good afternoon. My name is Fernando Mourão and I'll talk about our work entitled A Particle Swarm Approach to Mitigate the Diversity Accuracy Dilemma in Recommendation Domains. The context of this work is closely related to the well-known paradox of choice, a topic that has gained a plenty of attention in the past few years on both industry and academy. When buying an item, watching to a movie, listening to a song, almost always on the web, users face more options that they can effectively handle. For this reason, recommender systems has become essential to increase user satisfaction, retain these users over time in the system, or even leverage profits. We realized that helping a user to find the items that fits his or her personal interests became a core business feature. In this context, accuracy became the core quality measure for recommender system, but academy is aware that pursuing accuracy is necessary but not enough to effectively help users in many real domains. Success on this case goes beyond providing high accuracy. It includes new quality dimensions such as novelty, familiarity, unexpectedness, utility, diversity, among many others. So the new perspective is that accuracy is not enough, we should go beyond, and this work is particularly aligned with this perspective and has as main goal to find a new method that improves the item diversity while maintaining the level of accuracy achieved by the recommender system. Basically, we propose a post-processing approach based on the traditional particle swarm optimization to be applied in any recommender system that we see as a black box giving to us input recommendation lists. Okay, this goal is of combining accuracy and diversity is useful in practice because it usually generates a significant fraction of total revenues in many domains, but it's usually challenging because there is an apparent dilemma in balancing accuracy and diversity in many scenarios. This because usually when improving accuracy, we recommend more popular items. Existing strategies to increase diversity, on the other side, usually recommend less popular items, and consequently, accuracy is affected somehow in these cases. So our strategy is seeing this problem, this balancing, as a combinatorial optimization problem whose goal is to select from the set of m input elements a smaller subset of n elements that are the most diverse among themselves. And traditionally, we measure diversity in this kind of problem through similarity or distance metrics, considering a specific feature of my domain, okay, like cosine, etc. And the goal is to maximize this distance or similarity metric among pairs of items. Okay, so in summary, our proposal could be seen as depicted in this picture. So we consider a recommender system as a black box that gives to us input lists, higher number of lists of recommended items, and we re-rank these lists considering our objective function and generate as final recommendations to the user a subset of items that maximize the diversity with respect to the objective function. Okay, this objective function is usually expressed as a straight linear combination about two concepts, that's relevance, measured through accuracy, precision for instance, and diversity, measured, as I said, considering distance or similarity measurements, and we combine it then using a lambda factor that determines the weight of this each of dispersion in our objective function. Okay, and usually the relevance is measured considering a ranking relevance for each specific user, for example. So in this case, top items on the top of the rank will have more relevance than the other one. And another strategy to measure diversity that we will adopt here is considering, for example, a given feature like genre and see the coverage of distinct genres that the recommended, the list of recommended items have. Okay, so it's basically genre coverage in this case. Talking about the particle swarm optimization just a little bit, it is an evolutionary method that optimizes a given problem, and basically it tries to improve a candidate solution with regard to a given measure of quality. It solves a problem by having a population of solution candidates, particle, and moving them around the searching space according to a simple mathematical equation. So it's inspired on the birds, for example, and this kind of movements that we observed using many individuals in biology. Okay, and the particles movement is influenced by three distinct factors usually. Okay, its Q and position, so a particle have a starting position P0, the best location that this specific particle knows so far, and what they call a social component. That's the best global location that any position, any particle, has reached so far. Okay, so usually we combine this three information to determine what we call the movement of velocity of a particle. So a particle in a given particle y with d dimensions in the interaction k is determined by the k plus 1 is determined by its previous position plus the movement that it performs. And this movement we call it as velocity of the particle, and as I said, it usually contains three distinct information. So a local information, a global or social one, and a constant one that we have here to determine how each particle will search, will move on the search space. Okay. And in our specific context, how we adapted this general strategy of particle swarm optimization to diversifying recommendation lists. This algorithm explains that we use a strategy named team draft interleaving, and it consists basically of having a number of input rankings. In our case, we have three rankings. For example, a P0 would be a list of random number of items. P-best, the best recommendation that a particle have received, and G-best, the best general, as I said. And we can define a prior probability of selecting items from each of these lists, okay, in this W variable. And for each interaction, where the number of interaction is the number of items that we want to pick, basically all we have to do is select one of the input lists considering the prior probability we have defined. After we have selected this list, we randomly can pick one of the items present in this list, and put this item on the output ranking list that we trying to generate, and remove this item from all of the lists and repeat this process until we get n distinct items from the input recommendations lists. Okay, so it's a very simple approach that we use here. And now we're going to talk about the experimental analysis we have conducted. So we selected two data sets, traditional data sets of the domain. One is the movie lens 1 million for movies, and the other one is the Tiao data set, that's an e-commerce of DVD sales. Okay, both of them have ratings ranging from 1 to 5 stars, and we adopted the traditional train test partition using 70-30% for each of them. Okay, the metrics used to measure the quality was the traditional metrics of precision and genre coverage. Okay, so also we provided two variances for each of these metrics that basically considers relevance as to determine if an item is a hit or not. Okay, relevancy in this case, for example, we consider that a movie eye was relevant for a user if, besides watching this movie eye, the user assigned to it a score higher than his or her personal mean score. Okay, so we consider that besides watching, user should like the item to be considered as a relevant item. Otherwise, we just consider if the user watched or not, or evaluated or not an item, etc. Okay, and the baselines we consider three basic strategies available on My Media Lite library. Okay, and here we have the values found for each of the metrics we use it on the data sets. Okay, when considering the lambda of 0.5, that means that we give the same rate of relevance for both components, that's the relevance information and diversity. And we can see that while maintaining accuracy related metrics statistically equivalent after applying our post-processing strategy, we observed statistically significant improvements on the diversity related metrics here. Okay, and these graphics corroborate that they shows in the y-axis the accuracy, and the x the percentage of users. So it's basically the distribution of accuracy per user in each data set. And we vary here in the first column. We have lambda 0. That means that we consider only relevance here. In the middle we have lambda equals 0.5, and the left and the rightmost graphics are lambda equals 0.75. Okay. So in terms of accuracy, we observe that in most of the cases we cannot see significant difference between the baselines, the red lines, against the recommendation after the post-processing we proposed. And when we consider the diversity, we see a significant difference in the distribution, showing that indeed we can enhance diversity while maintaining the original levels of the recommendations. okay, the input recommendations. And just to visualize the type of change that the post-processing strategy can perform on the outputs, here we have a simple example of providing recommendation before our strategy. So usually we have similar movies like Star Wars 5 and 6, Indiana Jones, and on the right side we have recommendations after applying our post-processing strategy, okay? Here we can see a more diverse set of genres in this case. So as conclusion, we proposed a post-processing method based on an evolutionary algorithm. It was able to reorder recommendation lists generated by 3 distinct recommender systems and gained up to 60% in diversity while not losing accuracy. And as future work, our intent is to evaluate other different evolutionary methods, considering more recommender systems and data sets related to other scenarios as well. So thank you very much for your time, and that's it.